Hi, everyone. Thank you for coming today. Thank you to the sponsors, Domino, Plotly, our studio, and others for putting on this conference. Today I'm going to be talking about interactive visual statistics on massive data sets. My CMO always slaps my wrists and tells me I should say big data, but for y'all, I will change it to massive data sets. How many people here have tried to look at really large data? Great, but there's a lot who have not, right? How many people have actually feel like they successfully looked at a few million points and really gotten something out of the viz they didn't already know? Not as many hands, all right. So today I'm going to be talking about that particular topic and a tool that we've developed at Continuum to do that. I'm Peter Wang. I'm the co-founder of Continuum, and currently I serve as CTO. At Continuum, we've created things like Anaconda. I personally started the PyData conferences. We've created a lot of tools like Dask and Bokeh and these other things that people have been talking about today. But Datashader is one that doesn't get as much coverage, but I think is a very exciting technology capability. And so first, let me talk about what is the problem. And the problem is not that big data is, visualizing big data is hard. It's actually that visualizing big data accurately and well is, it just amplifies all the problems you already had with visualizing small data. So, so the standard plotting tools that we use, even on small data sets, already suffer from a number of visualization problems. Visual hallucinators, as some people call them, whatever they might be, and we simply have some deafness to kind of get around it. We have some tools of the trade we use to get around those kinds of things. But all those issues we run into, they're much harder or impossible to resolve with really large data sets. And so I'm going to go through just what I mean specifically by those things, so we're all on the same page, and then I'll show Datashader and how we use it to solve some of these problems. So the most obvious problem is one of overdrawing. How many of you use Matplotlib? How many of you know the order in which Matplotlib will render a set of data points given to you? You want to bet $100 on it? Who wants to bet on it? All right. I don't know. Not you. Not him, but anybody else. Right. Or Excel. Replace Matplotlib with Excel, with GNUplot, with ggplot, with whatever. Right? I ran into this as an undergrad. I was like, oh, wait a second. If I just change the order of the columns, I get different looking plots. Everyone runs into this problem. With small data, we're like, oh, well, maybe what I can do is this is the problem, right? Depending on how I draw it, the most recent color seems more predominant. And maybe if I'm really clever, I can set an alpha value if my tool allows me to do that. And the problem with setting an alpha value is that it's still not good enough. You can still have collision, you can still have saturation, it just takes a little bit longer to get there. So you've just kicked the can down the road. And for a single category, if you have 10, 20, 2,000 points, you can set the alpha level to the lowest possible alpha, and you will still end up in this problem. And so like what here, so if you have more points, it starts running into the same problems. You might say, well, I can reduce the point size then. I'll be very clever. I'll make the points smaller and I'll reduce the alpha. But this is a very difficult parameter to set because now your points are tiny and faint, which is great for seeing when there's a whole bunch of them together, not great for looking at outliers. Anybody here interested in outliers? Right. So it actually fundamentally, the techniques we use to get resolution in the core actually hurts us at the edge. The things that we use to enhance the edge hurt us at the core. It's a classical dynamic range problem. Most of the viz techniques we have, they suffer from not offering us good approaches for dynamic range. And so when you get the points down to be small enough, you're actually at multiple points per pixel, and at that point, you're actually doing something like binning. So we have developed, as viz people, we use binning, right? We use hex bins, square bins, all sorts of various things. We use circles and make these like really cool like diagrams that look really, really cool, but they actually dramatically reduce the amount of information density that we're getting out of our viz. And more importantly, I would say that the challenge is that when you plot big data, you actually don't know when the viz is lying to you. You don't know when it's omitting one outlier. That was the really important one. You don't know when it's just sitting there reiterating or reinforcing to you the models, the statistical model of the data set that you walked in with, as opposed to helping you validate or challenge it. So that's one of the biggest problems with viz. Like if you use Python or use R and use any of these kinds of programmatic tools, if you do the fundamentally wrong thing, oftentimes it will complain and throw an exception. There's not a single viz tool that I know of. There may be a few that offer advisement, but most tools do not error out on you if they're lying to you. They'll just do it. Okay, and we laugh, but we make life and death decisions based on these things. We make policy decisions for countries on these kinds of things. And as we start looking at more and more data, as we start trying to let the data suggest to us better questions, we can't do that anymore, right? The data and the viz tools are more than happy to reinforce what we think we already knew. So the Datashader approach started really as me trying to figure out how do I build a better server for web graphics. Because I took it as a given that I was not going to dump several gigabytes or terabytes of data into the browser. No matter how good JavaScript gets, that's not that useful. And so if I wanted to do rendering on the server side, but I wanted to present and interactively present meaningful data explorations in the client side in the browser, what is the right language for that? What is the right protocol? It's not JSON. If you think JSON is the answer, you don't understand the question, right? Because the question is, how do I specify what I want visualized without imparting so much statistical sort of prior on it that I lose the texture of the data itself? And so what we developed, what emerged from that line of thinking is a technique called data shading, but a tool called Datashader. And what it is it's a flexible and configurable pipeline for automatic plotting of large data sets. It has flexible plugins for different viz stages, and it really strives to prevent these common problems, overplotting, saturation, things like that. By providing a connection to Bokeh, we are able to provide a fully interactive experience in web browsers, even for very large data sets. And so that mitigates binning issues because we can kind of go into the data, zoom in, zoom out, things like that. And the other key, and I think the most important aspect of this, is that most of the tools that you use for visualization, they let you configure things like color and line style and fill pattern and alpha and things like that. What Datashader wants to do is give you this pipeline, make the viz pipeline first class, and let you write your statistics and put those at the very root of the pipeline. And so to make this more concrete, if you think about how you start off for most viz, you start off with a table of data. Then you do what we call a projection process, right? You basically pick something, to sit in the x direction, something to sit in the y direction. You pick your retinal variable mappings to your data sets. And at this step, oftentimes you filter down the data, okay? Once you've projected them into what I'll call the scene, then there's some kind of sampling or rasterization process. And that produces what we call aggregates. You can imagine here, we put in this raster grid, which could be the pixel grid that you want an 800 by 600 image or something. And in each one of those pixels, there could be thousands of points. So we create these aggregations, we create these bins, and inside each of those are all of your points. And each bin can yield some number of statistics. It could be raw counts, it could be the mean, the median, whatever it is. And then once we yield those counts for every bin, then we apply what we call the transfer function, the actual creation of some visual primitives and their visual aesthetic properties based on that. So this is kind of a little bit off in the infovis academic space, but for those of you who've done graphics for a while, you can probably see how most of these steps are kind of implicit in most of the tools you use. And hopefully by looking at this, you can also see how if we deconstruct this viz pipeline for large data sets, we are able to maybe solve some of these problems of overplotting and oversaturation. So let me go ahead and do the demos, and I'll just show you how this is done. So this is a data set that is, how many points here? 10 million points. This is flight paths. And so you see you have longitude, latitude, the origin, and the country of origin, which is categorical, whether or not it's on the ground, and whether it's ascending or descending in the velocity. Okay, so we're going to load these in, and we can then dump the plot of this thing. This is using Datashader. I don't want to get too much into the code of this, because that'll just really drag us down. But we're creating a canvas. We're creating line elements for these flight paths. And then we're just going to call transfer function.shade. That's part of the Datashader pipeline. And we're going to use the Inferno map. And so that gives us then a static image. Datashader is a library that can create static images. So it's not tied to Bokeh, although it works really nicely with Bokeh. So here we have a static image. It took 1.2 seconds to render 10 million points. And the thing about this is, oh, this looks really cool and pretty, and it looks kind of weird, like somebody scribbled all over Europe. But the key thing here is that Datashader does not lie to you. It has mapped the brightest value here to the greatest density of values, and it's mapped the lightest value to the lowest density. If we actually plot this, so here we're going to then actually load in Bokeh, the interactive image object, and we're going to add a tile source. And that tile source gives us this nice little overplotting on top of Europe, and you actually see what this looks like. And you see this is, I guess this is what, Paris, maybe? Something like that. Maybe that's London. No, that's London, right. So then what we can actually do here is we can just turn this to render all the categoricals, and we're going to take the count of categories, and we're going to map it with HSV. And so this shows you then all of these flights colored by origin, and notice that, so it takes a second here for it to kind of round trip the actual data into the browser. With the new improvements coming in Bokeh, in the next version of Bokeh, that'll be much, much faster, because a lot of the time is actually in the data encoding and decoding. But as we zoom here over London, notice as we zoom in, the data refines. That's the Datashader engine. You can actually see my cores running there. It's refining, and it's showing you more and more texture as you zoom in. You can see the holding patterns, right, of planes on approach to the London area. And notice, like, as I zoom out, that doesn't overplot, doesn't get turned into a giant mess. Well, it's kind of a giant mess, but that's just the nature of the traffic. But the Datashader system is, at every level of resolution, it's taking into account my viewport as an input. And it's doing a full table scan of the data. It's doing a full perceptually accurate mapping of this data set. I can go down here and say, well, actually, I don't care about the country of origin. I just want to know whether the plane was going up or down. And so this gives us red versus blue. And what we can zoom in here around London, I think this is actually quite pretty, is you can actually see that all of those circles are holding patterns indeed, right? They're red. There's as the plane is coming down. The blue, they don't really hold on the way up. They just kind of go up. And so it's a really nice little thing. And what's cool about this system is this is 10 million points, loaded into a notebook, a few lines of Python code, and I'm interactively looking at down to the individual trace level. And this is a live demo, knock on plexiglass, and it works great. So yeah, I think that's it for that one. Another data set that people here are probably familiar with and maybe tired of is the New York City taxicab data set. This is 12 million. We have a subset of it, so this is 12 million points. Just passenger count, pickup time, drop-off, pickup locations. And that's the table. And this is very important that you remember this. The columns, every single row here has a pickup and a drop-off location. So when I go and I render this, if I do a subsampling of it, 10,000 points, I end up with this kind of map, and overplotted on top of the map of New York, it's sort of subsampled, right? It's not that dense. If I go to just 10,000 points, however, at the full image scale of this data set, you can see it's overplotted, completely overplotted. And at this point, what I might do is go and start fiddling with alpha and pixel size, things like that. But if I use Datashader, I can just very easily set up in 3 lines a pipeline that maps from white to dark blue, the least to most dense collection of points, and I'm plotting the passenger counts, and I'm doing a linear color transfer function. And that takes half a second for this to run and create a static image. And there's the image, right? And what you notice with this image is that, oh, wait, hold on a second, what's going on here? You'll notice that here around, I guess, Penn Station and in LaGuardia, there's some density, but everywhere else is relatively white. And the reason is because if you look at the histogram of values and counts, there's a massive, the function is not very linear. And so you have a few, it's a long tail of few that are very popular, and most of the places are actually not very popular at all. So that's why so many of the pixels are white. So then what we can do is actually say, well, let's do a logarithmic transfer function instead of a linear one. And now you get something that looks a little bit more familiar, right? But why do we think logarithms are the right way to map this? Why is that the right transfer function? Now, some of the smarter people here in the room might say, oh, because of gamma and the human visual response system and all this stuff. And you're mostly right there. But the actual really great thing to do is to use an approach called histogram equalization, where we look at actually the total amount of energy, the total amount of data at any given level, and we allocate an appropriate amount of visual weight. And so with that, we get then a slightly different and very lovely map of this beautiful city. So then if we want to make it look really pretty, and make it interactive, it's a few more lines of code, but now you have, this is about 12 million points interactively in the browser, and you can see most of, let me actually hide the header, hide the toolbar. You can see this is actually quite lovely, but as we zoom in here, what will happen is you notice how the Datashader system, once we zoomed in, it remapped the brightest and the brightest points. It actually refined the density of data. And what you can see here is that Midtown, I think you can see it on the projector, Midtown is noisier. You see how it's grainier and noisier than the rest of New York, right? Why do you guys, anyone know why that is? Any ideas? There you go. So GPS, tall buildings and structures will obscure GPS signals, and that's how we get fuzziness. Now, what, if you didn't know that about this data set, can you think of what statistical function you would write to pull out that intuition about this data set? Right? It'd be very difficult. And the reason that I bring that up is because when you look at this, you can't not see it. When you viz all the data, it jumps out at you. You're like, why is Midtown all, did somebody smudge my monitor? No, it actually, that's the data, right? There's drop-offs in New Jersey, which I can believe, but there's drop-offs in the middle of the Hudson, which I don't believe, right? Those are the things that show up. And what's really nice is, of course, with Datashader, and this is just a little code example to show how we can overlay this on top of a map of New York. And so let's zoom in here and see where is this extremely dense spot down here that we saw. So obviously Grand Central has a lot of traffic right here. Yeah, so this is nice. So we can actually see. Also one other thing to point out about this before I go any further is if I zoom in to some of these really bright spots, I'm going to do it really quick so you can see how many points are within every single original pixel at the zoomed out level. Right? Datashader has access to the full data set all the time. And so as I zoom in even more, what you'll actually see is there's kind of this quantization grid of the points. And that's actually because the data set itself is a little bit truncated. And you can see that I don't know if you can see it there, but it's a relatively regular grid. These are things that pop out at you when you look at the data set, when you can view all the data. So one more cool thing that I can do, I talked earlier about the fact that Datashader is not just a way to throw all the data at the screen and hope that doesn't lie to you. It's actually a live pipeline that lets you write statistics on the data. So that's what I'm going to do. Here I'm going to shade the places where there are more drop-offs than pickups in blue, and I'm going to shade where there are more pickups than drop-offs in red. And I'm going to put them together, and here we go. Give it a second to build the pipeline. What it's actually doing here is it's actually using our Numba compiler, and it's compiling that Python expression into low-level machine code. Then it's going and running that machine code on the full data for every single pixel and shading it appropriately for us. And now we know something about this data that New Yorkers probably know quite well, that your cabs are going to pick you up along the avenues, and you're more likely to get dropped off on the cross streets. But what's really interesting about this, though, is if you look a little bit, there's some interesting structure here. If you look over here at Javits, you can actually see the pattern of traffic. You can actually see the cabs swing in to drop off, and then they pick up. At least that's what I'm guessing, because I don't see cabs like dropping off and then backing up to pick people up. But you can actually then infer traffic flow. Additionally, you can look over here, and if you don't know much about Queens, when you look at this picture, let me zoom out on this one, you might not be able to tell what streets in Queens are the main streets and which streets are less important. But if you bootstrap your knowledge through Manhattan and you look at Queens, you can actually tell, oh, here we go. We know where the popular streets are, because that's places where the cabs are going to pick up. And this is, again, looking at this data, if this was not New York, but this was some foreign country or something, you could bootstrap this kind of knowledge. Another really interesting thing is if you look here at LaGuardia, what you see is this pattern where the cabs are dropping off in the middle of a bunch of pickups, which seems kind of, here, they're kind of side by side, but here, it's right in the middle of it, which seems weird. Anyone guess what's going on here? Right, there's actually a two-tier parking structure there, right? Or two-tier terminal structure. So the pickups are happening above, the pickups are happening below, the drop-offs are happening above. And this is all knowledge we're bootstrapping just by rendering all the data, writing 2 lines of code, and then leveraging a whole bunch of other stuff that, a bunch of other libraries. So that's New York. We can also color based on time of day, hour of day when people get dropped off. That's kind of a high-level view of something we can do with Datashader there. We've recently added the ability to load raster images and render raster images and do data shading on raster. So this is looking at Landsat satellite imagery. And any of you who know something about satellite imagery, there's different bands that they image the Earth in, different wavelengths. And so we've loaded all this in using Raster.io, and we're going to basically just render the blue band. And here we have an area around Mobile, Alabama. If we zoom in, Oh, I zoomed in a lot there, sorry. But you can see actually the raster data, we're now at the pixel level of the raster data. As you zoom out, we actually get the full raster data set there. You can actually come down here and implement your own data normalization routine as well as the true color combination. So if you do all that, what we're going to do now is assemble the red, green, and blue bands using our own code, and we get then the true color image of this area, which is very lovely. This is because it's using Numba, because it's all Python code, you can customize this however you want to do some really interesting things with the raster data. Here, for instance, we're going to actually go and look at the raster data that's not intensity, but actually height, elevation. And so if you do a basic elevation plot, this is the elevation plot around Austin. And it's going from dark red to white to dark blue. So red is the darker area, is the lower area, blue is the higher areas. And so what we can do is then we can actually go and write our own little function for computing slope. Very simple function, and we get this. This is, again, all just computed dynamically on the fly from that raw raster elevation data. And you can customize this however you want to. You can actually go and say, well, I want to look at aspect. I don't want to just look at slope. If you look at aspect, you get that. And this is all this is just a few lines of Python code for each of these things. So this is actually dynamically, the Datashader pipeline is dynamically computing aspect ratio based on the functions I wrote off of this raster data, off this elevation data. That's actually Lake Travis there. If you combine slope and aspect together, this is actually I don't know how many people here do GIS analysis, but this is a very powerful way of getting a much better intuitive feel of the texture of the terrain. You can actually do this thing called hill shading, which looks at all these things together, and you get this really lovely topographic map. And this is not, again, I didn't have to rely on some big vendor, on some GIS experts to go and craft something. This is all just math code that's right there in the Python for me. And you can actually go and do something even better. If you want to actually look at, for instance, one of the ways that you can look at vegetation in satellite imagery is by looking at the ratio between the near infrared and the infrared channels. Sorry, near infrared and red channels. And so if you implement this, it's called NDVI, Normalized Difference Vegetation Index or something like that. You can actually go and look at, this is an area around New Mexico. In green are the areas that are vegetation. Purple is non-vegetation. And I did that by writing, actually I have the code here, I think. This is the code for the Normalized Vegetation Difference Index. It is a few lines of Python code, of course, with a numbajit operator on top of it. This is the kind of thing that we can do with Datashader now. And the one last thing I'll show is looking at census data and what we can do with that. So this census data set, I think, is about 300 million points. All these, by the way, are running locally on my laptop. I only have this tethered to my phone to load up like the map tiles, things like that. So all of them are simultaneously loaded on my laptop. I apparently have Crash Plan running over my phone in the background. One second here. Pause all backups. But this is all running just on a standard MacBook Pro. So this is 300 million points of the census data set. And once we've loaded it up, we can actually go, and I won't go and walk through all the code, but this gives you a view of the population of the United States, colored by race, and data shaded. 300 million points interactively in your Jupyter notebook. We can come here and look at New York and see if it matches with y'all's intuition about the demographics of your fair city. Let's see here. How many people here are local to New York, actually, out of curiosity? Actually, a lot of people who are not local to New York. Great. So it's cranking away. This is also using, in addition to using Numba, it's also using Dask. So it's actually going and parallelizing the work. That also means that it can use Dask distributed and run remotely on a cluster. I'm not sure why this is taking a while to transfer the data over to the client side. Run, Dask, run. There it is. Okay. Again, a lot of this delay is because of the round-tripping of the raster data from the server to the browser. That will get much better in the next version of Bokeh. As I zoom in here, you can actually see what's really nice about this. Again, the Datashader concept is render all the data. Just render all the data, try to do it perceptually accurately. And when you do that, what you get is you get a view into the texture and the gradations in your data set. And so you can actually see here Blue, oh, so let me give you a color key. Blue is for white, Caucasian, I guess. Green is African American, red is Asian, and the yellowish color is Hispanic. And so one of my favorite parts in this map to highlight is up here on the upper east side, where you have a hard line where the white people don't go past, and you have Spanish Harlem as differentiated from Harlem. You have Rikers Island here. You've got, I guess, Queens and Flushing over here. You see all this stuff in the data. It's just there. Just like with the whole avenues versus cross streets, it's just there in the data. We have actually a better census plot that shows you can actually start asking questions like, show me all the places in the United States where there are more black people than white people. And you can change the equation. You can say, well, 20% more black people than white people, so on and so forth. So what's nice about this also is that this is Datashader, not just tied into Bokeh, but actually tied into another visualization tool we built a continuum called HoloViews. And so it's actually being scripted through the HoloViews interface. And so all this is live. These notebooks are published. They're out there on Anaconda Cloud. You can just play with them. But what we can do is we can load in the districts, the congressional districts of the United States, and render those. And what that gives us is this really interesting plot that doesn't actually show the races. So why is that? Let me try this again. Let it run. This is actually really, really interesting. And it's actually somewhat relevant to the recent election, I suppose. Took 3 seconds to render. It takes some time to round trip it here to the... Oh, okay, here we go. Oh, this is tied to the other plot. Okay, so what we're seeing here is the congressional districts overlaid on top of the races. Do you notice this cut right here? Isn't that interesting? But it gets better, because that's just New York. Let's go and look at Baltimore. People are laughing. This is Baltimore. And what's really interesting about this, I'll give it a second to render, this is legit gerrymander. Like there's no like Voronoi, there's no like distance minimization. There is no function that this shape optimizes for except for particular voting outcomes, right? All of us can look at that and see that. And as soon as the compute comes back, you can see actually how hard it cuts across the racial lines. Give it 1 second here. There it is. So what's really amazing about this map is, again, remember, blue is white people, green is black people. There's some Asians over here, but they don't really matter. Anytime, of course Asians matter. All Asians matter. But actually, if I click, check this out though. If I click anywhere that's green, pretty much, look at what congressional district it's in. If I click on a blue, guess what it is, right? It's just amazing. So you can basically click on color and you can actually see, if you start zooming in on this little boundary right here, you can actually see how hard it cleaves right there. It's absolutely amazing. So this kind of interactive visualization is possible with just a few lines of Python code, completely based on open source tools, running completely locally here in your notebook. And you can actually even go one step further and build interactive tools like this where you have drop-downs. This is the nice thing about HoloViews. You can have drop-downs here that actually select for different races, and it shows them across the United States. You can zoom in and out and play with that. So with that, I think I'm out of time. And I'll be over at the Continuum table. If any of you have questions about this, you want to talk about using this in your projects and things like that, would love to hear from you. Thank you very much.